Hello, it's a pleasure to be here. I'm so honored to tell you about my work in reading and language development, and I want to thank Dr. Wong and the colleagues in the Dr. Stanley Ho Foundation for inviting us. You heard a little bit from Dr. Luby already about brain development and behavior. And I want to highlight again that a lot of brain development happens before we're even born. So we know that many genes that affect things like reading and language development actually affect neuronal migration in utero. And so a combination of genetics and environment, even before we're born, begin to shape our brains for reading and language. It's also certainly the case that much of reading and language development happens after birth. And so our early experience during those sensitive periods for language affect our later reading and language ability. But this also continues through life. Parts of our brain are maturing, many of you still well into your 20s. And the frontal cortex that's involved in language is especially long maturing and experience dependent. Because some of this happens in utero, the brain comes wired for language. As soon as we can measure babies moments or hours after birth, or now with new MRI and MEG technologies, even while they're still in utero, we can see that the brain is left lateralized for language development. This continues through childhood, and most children learn language quite easily on a predictable timetable. Whether you're in Macau, Hong Kong, Chicago, you say your first words around 12 months and two-word combinations around 18 months and things like that. So for most children, language comes quite easily. But there are some things that can make language learning more difficult. For example, if a child is irritable and has trouble regulating their emotions, that can affect their language development. And family factors such as reduced language input can also meaningfully affect language development. So our brains are wired for language, and language happens pretty predictably, but our brains were never born to read. So this is little 5-year-old me who was already reading, but my brain was not wired that way. There are no genes that are only specific to reading. There are a genetic basis of reading, but no genes dedicated to reading. And there's no one part of our brain when we're born that is specialized for reading. We develop some regions that become more specialized for reading as we learn to read, but when we're born, there's no one part of the brain that's devoted to reading. Because that's the case, we have to take our parts of our brain for language, for visual processing, and other processes, and sort of craft a reading circuit. And each one of us must do that as we learn to read. And this means that each of our brains are a little bit different as we read, and it makes a lot of opportunities for reading development to not go well. So any one small process can be wrong or not working well, and that can importantly affect reading development. This is sort of a scheme of the many processes that go into reading. We think of reading as being one of our first jobs that we learn as children, but it's quite a complex task. So at the top here, we have the many processes involved in language, so semantics or the meaning of language, morphology and syntax, and language comprehension. And then we have processes that are specific to reading on the bottom as well. So seeing the visual features, especially important in logographic languages like Chinese, matching letter patterns, and translating the written language into spoken language, graphemes to phonemes. All of these are affected by our executive functions, the automaticity, and memory processes that support a lot of our cognitive functions. And when we have to speak or read out loud, articulation is also important. So all of these things are involved. They all have to be working together like a symphony. If any one instrument is out of tune, the whole thing can sound not so good. So all of these things have to be working together quickly and automatically for language or reading development to progress well. When it doesn't go well, we end up with children who have language or reading disorders. And I want to make sure we're on the same page in understanding what I mean when I say language disorder or reading disorder. So a developmental language disorder, often called specific language impairment in some groups, is essentially an unexpected difficulty learning spoken language. And dyslexia, or reading disorder, is an unexpected difficulty with learning to read. Importantly, dyslexia is not a visual problem, as is a common misconception. Both of these are only the appropriate diagnosis when they're not caused by a lack of cognitive ability, sensory or perceptual deficit, a lack of opportunity or exposure, or a lack of effort. So essentially, if a child has a healthy brain, a supportive environment, and they're still having difficulty learning reading or language, that's when we would diagnose them with a primary language or reading disorder. It's not so easy as though just giving one of those diagnoses. One of the big challenges in our field of diagnosing language and reading disorders is that there is no single one test in the US or in most countries that we use to diagnose these disorders, or a certain score on any given test. It's really based on clinical impression and the many factors coming together. Because there are all those complex processes that I just showed you, it's also the case that there's not one single cause of any given language or reading disorder. And because of those different causes, there's not one set solution. We can't just say, well, you have this diagnosis, here's the appropriate way to intervene. So there's a real complexity that makes early diagnosis and intervention challenging. Another big challenge is that we have what I would call a wait to fail model of diagnosis of language disorders. So this is sort of a prototypical cartoon of the way language development happens. In typical kids, they're progressing all along, but we have a group of kids who are called late talkers. And at 18 months, if a child has fewer than 50 spoken vocabulary words and isn't yet combining words, we call them a late talker. We don't call that a language disorder yet, because about half of those kids go on to be typical talkers. They're remitted, essentially. Without any intervention, they catch up on their own. The other 50% or so of late talkers have persistent language problems, and we've now waited, even though we were worried about them. Often they don't get any intervention, and they have that kind of slow, low trajectory where they're not going to catch up with their peers. We see the same thing in dyslexia diagnosis. In the US, at age 5 in kindergarten, children are learning pre-reading skills. They're learning letters, they're learning phoneme awareness, and these building blocks of later reading development. At age 6 or first grade approximately, they begin learning to read. Age 7 or second grade, we expect that they're reading accurately. And at age 8, crucially, they make the switch from learning to read to reading to learn. And they're not just learning to read anymore, but they are learning their other subjects. They're learning math and history and social studies from their reading. And they're also, through all of that reading, gaining vocabulary and background knowledge. Unfortunately, we don't diagnose kids with dyslexia typically until they've failed, until we expect them to be reading accurately and fluently. But we know that intervention is most effective when their brains are more plastic and when there's a smaller gap to close between the poor readers and their typically reading peers. So the goal of much of my research is to try to shift to an earlier and more accurate diagnosis of reading and language disorders by assessing things not just in behavior, but looking at the brain as well. So rather than waiting for this 8-year-old girl to be struggling, to feel the negative socio-emotional effects of being a poor reader, what I'm hoping we can do is do something like a brain scan in kindergarten, or a more nuanced type of assessment in preschool, and maybe even go back as early as an EEG in toddlerhood, or assessing the parents shortly after birth to give us indicators of which children are at greatest risk, so that we can give them that intervention early when it's most effective, and also, as you heard from Dr. Luby, more cost-effective. So we know from years and years of studying behavior that we can't assess kids accurately enough to diagnose before we've waited for them to fail. So maybe adding some brain measures can help us do this. So I'm going to walk you through several studies that my colleagues and I have done to look at early indicators of brain differences, primarily in children with dyslexia or at risk for dyslexia. There are some major challenges here, though. There's huge variability within each person. So if I took any one of you and stuck you in my MRI machine or EEG and then had you come back tomorrow, your brain would be a little bit different for a lot of reasons. You might have had an extra cup of coffee this morning, or you might be in a different mood, or a lot of things can affect our brain processing. So individuals vary quite substantially, and you each have very different brains. Everyone's brain is different, part of what makes human beings interesting. So those are two big challenges. It's also the case that for most of our brain imaging measures, people need to be relatively still. This is very true for MRI and somewhat true for EEG and ERP. And so we have the challenges of keeping wiggly little children still so that we can look at their brains. It's also the case that the tasks that we tend to use in neuroscience are not the types of things that people do in real-world situations. So you might come in and do a study where we put faces up one after another on the screen and ask you questions about them, like what are they feeling, or things like that. But that's not something you have to do in everyday life. So many of our tasks are things that are sort of artificial and experimental and don't match what we do in the real world. So we're trying to start to change that a little bit, and I'll tell you about that at the end. I want to share this slide with you from colleagues at Yale University and Haskins Labs that studied speakers of different languages. And they had people who spoke Spanish, English, Hebrew, and Chinese come into the scanner and listen to spoken language or read printed language. And what they've shown here is printed word brain activation in blue, spoken words in green, and the overlap used for both processes in purple. And I hope that what you see from this is what I see is a lot more similarities than there are differences. So even in a language like Spanish, that's a one letter to one sound correspondence, to English, which is a little bit more tricky, to Chinese, which has very little sound to letter correspondence and a logographic system, the parts of the brain that we're using are generally quite similar. And you'll see that we're using both hemispheres, we're using regions throughout our brain. So I wanted to start out with this to say that I'm going to talk about research on children who are learning English, but I think that we can take a lot of this understanding how similar our reading brains are across languages and think about it applying pretty well to Chinese and other languages as well. So here's sort of a simplified cartoon version of what I just showed you of the reading network. So the regions that we know are primarily involved in reading are the inferior frontal gyrus, the temporal parietal region, including the inferior parietal lobe, supramarginal gyrus, and angular gyrus. And then tucked down underneath your brain in the fusiform gyrus is a region called the visual word form area. And this region, only as we learn to read and gain experience with print, becomes more active for written language than for any other type of stimuli. So we weren't born with this, it was there, it just wasn't specialized for reading yet. And importantly, we also have a white matter tract, or kind of a highway in the brain, called the arcuate fasciculus, that's shown here in green. And all of these regions are very important for reading, and each one has been shown to be altered in dyslexia in one study or another. In this meta-analysis by Fabio Richlan and colleagues, though, they examined a whole bunch of different fMRI studies and found that there's actually quite a variety or heterogeneity in the regions that are implicated to be different in dyslexia. So you can see some of the ones I just talked about, the middle and superior temporal gyri, the inferior parietal lobule, and things like that. But across these studies, which were importantly across different languages and using different diagnostic criteria, but they're in a way more different than they are similar. So this is one of the big challenges, is sort of trying to get to the root of what's common in all studies versus artifacts or things that are different study to study. So going back now to kind of understanding what's going on in kids with dyslexia. A few years ago, we did a study where we wanted to see if children with dyslexia were exhibiting a pattern of brain activation that was qualitatively different from their typically reading peers, or whether they were sort of lagging behind and doing the same thing as typical readers, but at an earlier stage of development. And so what we did was we had kids who are 7 to 12 years old come into the lab, and they did an auditory rhyming task in the MRI scanner. So they heard 2 words and decided if they rhymed. There was nothing to read. It was all auditory. And we saw that in the typical reading controls, they activated this frontal region, the inferior frontal gyrus and interdorsolateral prefrontal cortex, and that was what they used to do this task. In the middle column here, the kids with dyslexia, what you're actually seeing is a blank brain. And it's not that they're not using their brains, it's that all of the kids with dyslexia were using different brain regions. And so when we average the whole group together, it looks like there's no activation in the brain, but it's just that they're each sort of taking a different pathway. And so when we take the average, there's no average region that they're using. And when we directly compare the control group to the kids with dyslexia, unsurprisingly, they're different in this frontal region. What we could do now, though, is take some younger kids who were matched to the kids with dyslexia in terms of their phonological awareness ability and see, do these younger kids who are at the same level in phonological awareness, which is so important for reading, do they look like the older, typically reading controls, or do they look like the kids with dyslexia? Here's what we found. The controls positively activate this region, and the kids with dyslexia actually are deactivating this region compared to rest. So they're sort of turning the region off. But the kindergartners, much younger, 5 years old rather than 7 to 12, they looked like the older typical readers. So this tells us that dyslexia isn't just a lag, kind of that they're the same but further behind, but a qualitative difference, a real use of different pathways in the brain. Another thing I'm really interested in is the variety of profiles that we see in reading development. So I mentioned all of those possible things that can go wrong. And my doctoral advisor, Marianne Wolf, proposed several years ago an idea called the double deficit hypothesis, that a deficit in either phonological awareness or rapid automatized naming, which is naming an array of familiar items like colors or objects or letters, could cause dyslexia. Either one of those on their own were enough, but if you had deficits in both of those abilities, you would have the poorest reading ability. And no one had ever separated out children who had different types of deficits and looked at their brains before. So in this study, we had children who were typical readers, children who had a deficit just in phonological awareness, those who had a deficit just in rapid naming, or the double deficit in both. And this time they were doing a reading task where they read 2 words and decided if they rhymed. And what we see in the brain is that the kids who had the phonological deficit showed differences in their brains in the inferior frontal gyrus and the inferior parietal lobe, key areas of the reading network, as you now know. Interestingly, the kids with rapid naming problems showed a difference in the right cerebellum. And when I talk about this, people usually say, but I thought the cerebellum's about balance. And the cerebellum's actually about a lot of things, but one of them is timing and integration of timing processes. And so to be able to name each of those letters quickly, or to be able to read quickly and fluently and accurately, we need to be able to coordinate that timing. So it actually wasn't too much of a surprise to see this difference in the cerebellum. So this tells us that even when you have kids who have overall the same reading ability, depending on what process is impaired underlying, their brains look different. The variability in these profiles might be one of the reasons that we can't yet use brain markers. Just like in depression, we can't use a brain measure to diagnose dyslexia. We need to use behavioral assessment. And so we need to be able to assess all of these things accurately and determine the causes versus the consequences. So in these kids who are already with dyslexia, we don't know if things in their brain are different because they've had less reading experience, because they don't like reading, or if they've already been there from the beginning. So I'm going to show you some studies where we've looked at pre-readers to see if low reading ability causes less reading experience and causes brain differences, or if there have been brain differences there all along that led to lower reading ability and less reading experience. In the US, we know that a child who's in the 90th percentile for reading ability reads as much outside of school in 2 days as a child in the 10th percentile reads in a year. So as that compounds over time, you get these massive differences in how much reading experience kids have. And so when we look at older kids or adults, we don't know what's the effect of dyslexia having always been there or differences in experience. So what we're hoping to do is see if there are brain measures that can give us a clue as to who's going to have dyslexia even before they learn to read. My colleagues Fumiko Heft and Meki Vandermosten and I published a meta-analysis, so a study of studies a couple of years ago, where we looked at a bunch of other work, fMRI work on pre-readers, and saw where in the brain are pre-readers who go on to have dyslexia different than their typically reading peers. And you see these regions keep popping up again and again. The left inferior parietal lobule and the left fusiform gyrus or visual word form area already in pre-readers are different if those children go on to have dyslexia. We've also been very interested in the white matter tracts that I mentioned. I mentioned the arcuate fasciculus, that's shown here in yellow, connects our temporal and frontal language regions. 2 other tracts that are important for reading are the superior longitudinal fasciculus, shown here in purple, and that, rather than finding its way down to the temporal lobe, finishes in the parietal lobe, and another tract called the inferior longitudinal fasciculus that goes down to the visual word form area and through to the temporal lobe. So in this study, we were looking at pre-reading kindergartners and both the size and the organization of these tracts. Our measure of organization is called fractional anisotropy, or FA, and it tells us essentially how well organized is that tract. Is it myelinated? Are all the axons going in the same direction? So we're looking at these tracts in these kiddos with dyslexia, and what I'm plotting here, we're looking at these tracts in pre-readers. We don't yet know if they have dyslexia. We're plotting their score on a blending words test. So this is if I said to you, what word do these sounds make? K, a, t, cat, right? So this is an important pre-reading skill. And then on the y-axis is their FA, or the organization of their tract, and higher is better. So we see this strong correlation already before these kids have learned to read in this tract that's crucial for reading and language and their pre-reading abilities. And one of the fun things we can do is pick out 4 example kids who vary in their pre-reading ability and look at their tract. And you can see that as you go from a score of 0 up to a score of 11, you go from a small little tract to a nice big robust tract, and the bigger tracts also have more warm colors, which indicate areas of greater organization. So already before these kids have learned to read, this tract that's important for reading is less well organized and smaller in kids who have low pre-reading abilities. Then, even cooler, my colleagues at Boston Children's Hospital, Nadine Gaab and her team, looked at babies who are at family history risk of dyslexia. So they had a parent with dyslexia, meaning that they're at much higher risk of dyslexia themselves. And in the first year of life, the babies with a family history of dyslexia, plotted here in blue, have lower FA across the whole tract when we divide the tract into little pieces than their counterparts who have typical reading in their parents. So this really tells us that this is probably something that's always been there and is causal to dyslexia rather than being a consequence of reduced reading experience. We also see, again, echoing the theme of how the environment can be so important, that parent education actually mediates the relationship between the brain and these reading indexes. So these were kids that we scanned in kindergarten and second grade. We looked at their brains in kindergarten and saw that for those kids who were higher SES, so higher socioeconomic status, there was a mediating relationship of their mother's education on the brain, but there was not a relation in lower SES kids. So we also could tell then how important these different predictors were in predicting their second grade reading ability. So phonological awareness was the most important, but the second most important predictor was the intersection, the interaction between that tract volume of the inferior longitudinal fasciculus and mother's education, and then mother's education alone, rapid naming, and the tract alone was not very important. So these kids are, the brain is important, but the environment is also important. Another indicator that we're very interested in is the ERP mismatch negativity, or MMN, and Dr. Urs Maurer at CUHK has done some work on this, looking at this measure in kindergarten. So kids just listen passively to speech sounds, and every once in a while they hear a different one, and how well their brains are attuned to speech sounds and picking up that unusual speech sound is the best predictor of their 5th grade reading ability, better than any other behavioral measure that they administered. And the neat thing about this is we can measure it very shortly after birth, as soon as we can kind of get EEG electrodes on a kid. So colleagues in Finland have measured this 4 hours after birth and find that it correlates with later reading ability. So this is something that we're collecting now. So knowing all of these things, that the brain differs in children who are at risk for dyslexia, how do we bridge from this research to practice? So we know that the brain is different, but what we haven't been able to do yet is take these indicators, whether it's the tract measures or the mismatch negativity or functional activation, and validate it in larger and multiple samples. So we haven't really been able to take something from one lab and apply it broadly and use it in a clinical or diagnostic fashion. In part, one of the challenges here is how different many of our samples are, ranging in SES, mental health, home language, and things like this. So I think a big challenge for our field is to take these things that look like good predictors and really test them out in diverse samples across universities, across the world, and make sure that when we find a predictor that it really works for everyone. Once we do that, we need to make sure, and I know that a lot of you are teachers or clinicians or speech-language therapists, that we're helping parents choose evidence-based interventions. So the interventions that we choose should always address the child's areas of difficulty. Once we've done that beautiful assessment that looks at all of their areas of reading, we should target those areas directly and not things that are peripheral, like visual functions or motor things. So essentially, if a child has reading problems and we're putting on colored lenses or having them jump on trampolines, that's not addressing their core deficit. It's addressing something else. And these are two things that parents are very tempted to do because it seems like a quick and easy fix. But with something as complicated as reading, the fixes aren't quick or easy. So we want to make sure that the interventions that we choose for children are in their area of difficulty. I want to tell you a little bit about where we're taking this now in my lab. One of the things that we're looking at is, I showed you that trajectory of the late talkers and some who catch up and some who have persistent difficulties. And we're looking at their brains, both in terms of their mismatch negativity and using a brand new paradigm, a naturalistic paradigm, where a child and their mother come into the lab, both wear EEG caps, and they interact naturally and play with books and puzzles like they normally would. And we can see if the child's brain is responding to their parent's language, and also see actually if their brains are more synchronized or similar when they're communicating versus not. We're also doing this paradigm in children with autism to see if this could be something that could be an early indicator of autism diagnosis. So we're very excited about this new way of looking at the brain in a more naturalistic setting. So with that, I'll thank you for your attention and my lab members and funders for supporting this work.
好多謝 Professor Norton 嘅，我相信大家都會有好多問題嘅啦。我哋盡量爭取時間嚇，因為跟住嗰兩個 talk 仲精彩，一個係講點樣同細路仔一齊閱讀，另外一個就係講中外父母對子女嘅期望造成嘅壓力。咁所以嗱呢一輪咧，大家有冇咩問題請舉手嚇，我盡量爭取時間俾大家多啲問題嘅。有先生先。
I'm most interested in this thing. But you talk a lot about seeing the thing. Suppose I learn through listening, hearing, do without seeing. Would that make any difference? Bypass your
in terms of reading ability?
Yeah.
Yes, we know that the most effective interventions for reading ability combine both spoken language and the visual aspect of language. So when we teach kids, we start out by teaching them to identify the sounds of spoken language so they can match them with written language, and also the meanings of words. And being able to bring together the sounds of language, the meanings, and the written piece is kind of the holy grail. We need to have all of those merged, so the best reading programs and interventions actually do bring together the spoken sounds and the written language.
Hello, Miss. Just want to ask, for you talking about dyslexia, I would first assume it's based on the learning of English. And I want to ask, like in Asia, most of our students are in the mother language of Chinese. So would there be difference for a second language learner in acquiring dyslexia, having some difference in either diagnosis or fMRI or EEG, something like that?
Good question. So anyone around the world can have dyslexia. I often get asked, oh, I heard there's no dyslexia in Norwegian, or there's no dyslexia in Japanese. But the way we define dyslexia is just an unexpected difficulty with reading. It can really occur in anyone, and there are always going to be people for whom learning reading is a little bit more difficult because these brain processes are altered. If you're learning to read in a second language where you don't kind of have that native-like familiarity, it's going to be even more challenging. We don't know as much about, we wouldn't really call it dyslexia if it's just unfamiliarity with the language. So we tend to focus on people's reading in their native language when talking about dyslexia. Does that answer your question? Thank you.
Very impressive work. Just for the last slides you showed for the hub scanning, the social interaction between mother and the children. What kind of design you used? Is a free communication or just use some kind of emotion or neutral word, or what kind of design?
Good question. So during the parent-child interaction, we set up some different contexts to try to get different levels of communication and interaction, and we go through and microcode moment to moment the video, which is time-locked to the EEG, and code if the parent and child are communicating, sharing attention to each other or to an object, or we set up a context where the parent fills out some forms and the child plays. So it's by going through and moment by moment kind of coding what state the dyad is in, and then comparing the EEG during those different states.